This is Captain Chaudhari. In my series of videos on basic ship stability calculations, I was doing the bilging in recent times, and I did a lot of numericals on midship compartment. The numerical is from my book, Complete Ship Stability. There's this length of box vessel 140 meters, breadth 21 meters, draft 7.2 meters, even keel. Midship compartment is of length 18 meters. It has got cargo permeability 70%. But the midship compartment is divided in port, starboard and center divisions by 4.5 divisions. The port and starboard compartment is of 5.25 meters width, and the breadth of the middle compartment is 10.5 meters. The kg of the ship is 8.501. We need to find out what is the GM of the vessel. So let's draw the vessel as per description. It's 21 meters in breadth, and here is the midship compartment. And if I try to draw in 3 dimensions this portion, it would appear like this. Or if we look at the plan view, here is the midship compartment, and this is the center line of the ship, and you have a compartment of width 5.25 here and 5.25 here. Right? This damaged compartment. So the initial draft is 7.2 meters. So what is the lost buoyancy, right? The length of the compartment is 18 meters. This is 5.25. So lost buoyancy would be, first of all, I'll have 2 outside the bracket because there are 2 identical compartments. It is 18 into 5.25 into 7.2 into 0.7. So that is the total lost buoyancy. 2 into 18 into 5.25 into 7.2 into 0.7. So lost buoyancy is 907.2 meter cube. Okay, now intact water plane area will be total minus loss. Total water plane area is 140 into 21, and lost water plane area, look at this, it is minus 2 multiplied by 18 into 5.25. So 140 into 21 equals minus 2 into 8, 2751 meter square. So sinkage is going to be lost buoyancy upon intact water plane area. So 907.2 divided by 2751 gives me 0.3297 or something like this. You can say 0.330, 0.330. So the final draft is going to be 7.2 plus 0.330, that is 7.530. Because it's box vessel, and because the damage is vertically uniform, because between the final water level, that is somewhere here, between the final water level and the keel, there is no obstruction, there is no intact buoyancy, there is no watertight flat. So we can say that KB1 is half of the draft. So that is 7.53 divided by 2 gives me 3.765. KB1 is equal to 3.765 meters. Now we need to calculate the BM. Now to calculate the BM, what we do is our strategy is going to be same. Now to find out the BM transverse is equal to residual moment of inertia of water plane area about the center line divided by V intact. Residual moment of inertia is total moment of inertia about the center line minus lost moment of inertia about the center line. So total moment of inertia is 140 into 21 cube upon 12. That is the total moment of inertia. We minus. Now what is the moment of inertia of this portion about own axis is given by 18 into 5.25 cube divided by 12. Now this is the moment of inertia about the own centroid. Now the width of this compartment is 10.5. From here to here is 5.25. Now from here to here is half of 5.25. So 5.25 divided by 2 equals plus 5.25 gives me 7.875. So the distance from the own centerline axis to the common centerline axis is 7.875. So can we say that we will remove that moment of inertia which is lost from here and here? So what is the loss about own moment of inertia? So it is 18 into 5.25 cube upon 12, and if I need to take this to the common center line by adding plus AD square, it would be 18.25. It will be 18 into 5.25, that is A, into 7.875 square. But we have not lost everything. The loss will have to be multiplied with permeability. Wherever we talk about loss, we also multiply by permeability. Divide by 140 into 21 into 7.2. So this is what we have done in this particular question. What we have done is we have found out what is the loss about own centerline axis, own fore and aft axis, but we don't want loss about the own axis. We want loss about the common axis. So we'll have to transfer the loss from here to here. The distance to travel is 7.875 meters, and we will use the principle of theorem of parallax. So we can see this picture. This is the plan view. This is the lost or damaged portion. This is fore and aft axis passing through the local centroid. We can find out by formula the loss of moment of inertia about own axis, because the moment of inertia about this axis multiplied by 0.7 will be the actual loss. But we need to transfer the lost moment of inertia to the common center line. Let us see how we do it. The total moment of inertia is 114 to 21 cube upon 12. The loss of moment of inertia about own axis is 18 into 5.25 cube upon 12. Of course, we'll be multiplying with 0.7. And when I take this moment of inertia to the common center line, I use AD square. I have to add AD square, right? But because the loss is coming from both the sides, the contribution is from both the sides, I multiply with 2. So let's do the calculations now. This whole thing divided by, I get 4.702. 4.702. This is the BM transverse. KB1 was 3.765. The total is 8.467. That is km. And kg, as you know, by the constant displacement method, we assume that the kg is not changing. 8.501. Oh my God. The GM that I will obtain is negative GM, and that is minus 0.034. So it is possible that after bilging the GM becomes negative, and this will happen if the B does not go sufficiently up, but the loss of BM is more than the rise of B. So in any situation where the stability is doubted, what can be done? There is a golden rule that the weights are welcome at the bottom and the buoyancy is welcome near the waterline.